Bilging problem here where we're again box-shaped vessel, given length, breadth, draft, kg, MCTC, with a forward end compartment, length 9.3, height 7. It extends the full width of the vessel. We want to calculate the drafts if the compartment is bilged. Always do a sketch. Now from the sketch you should be able to see, and I've done a fairly basic one here, because our waterline is intact, and it's intact because the height of the bilge compartment is 7 meters. Our draft is 7.2, so as this gets bilged and we sink further down, so our draft increases, you can see that our water plane area is intact. Because the water plane area is intact, our centre of flotation does not change. Now it's 124 meters in length, so our LCF is 62 from the after perpendicular, if you like. So 62, 62. It doesn't change. That's an important fact because when it comes to apportioning the trim, it's simply half and half. Half forward and half aft because the centre of flotation hasn't changed. And then you also have to bear in mind the trimming lever. Okay? Now the trimming lever is from the centre of flotation to the centre of the bilged compartment. So you can see that that trimming lever is not going to be 62. 62 is the total amount. It's going to be 62 less half the length of the compartment. So just establish that fact in your mind straight away first of all when you do a sketch. Is our water plane area intact? Yes it is. So the LCF, the position of the LCF does not move. Okay. So as always with bilging problems, let's work out the sinkage. Volume of lost buoyancy is going to be the 9.3 multiplied by 21, which is the breadth, multiplied by the draft of 7. Sorry, not the draft of 7, multiplied by 7, which is the height of the compartment. So 9.3 multiplied by 21 multiplied by 7, because it only goes up to there and the draft is 7.2, it can only be a maximum of 7. So that's our lost buoyancy. Intact water plane, 124 times 21, 124 by 21, because our water plane is intact. Okay, that's important as well to establish that fact that it's actually intact, so it's simply the whole amount, 124 by 21. Sinkage is lost buoyancy over water plane, intact 0.525. There's our new draft, 7.725. What we have to do now with that new draft, we have to then work out, okay, we've sunk down to that, but because we're bilged forward, we're not going to be at even keel, we're going to be trimmed, and we're going to have to work out how much trim forward and aft. Now the buoyancy lost is the volume of the lost buoyancy multiplied by the density of the water that you're in. So that gives you the weight of the buoyancy lost. The moment, trimming moments, is always a weight times a distance. So the weight is the weight that we've just worked out here, 1401, which is the weight of the buoyancy lost. And the distance, as we talked about earlier, it's 62 minus 9.3 over 2. So half that distance there to the centre of flotation across is our distance of the centroid, which is 57.35. So now we've got our total trimming moments here. The change of trim is simply trimming moments over MCTC. So our change of trim is 574 centimetres, 5.74 metres. And we now get the trim effect aft and forward. Well, as I said earlier on, because the centre of flotation hasn't changed, you simply split it into two. So there's our initial draft written down. That's the sinkage, which takes our draft of 7.725, and then we apply the trim effect. Obviously forward is plus, aft is minus, because we're going to be trimmed by the head, and gives us final draft 10.595 forward, 4.855 aft. So important point now really is establishing whether your water plane area is intact. Once you've established it's intact, you can then see that the centre of flotation position isn't going to change, which means that the trim is simply split in two, but it does have a bearing on the length of the trimming lever when you're working out the trimming moments.